Hello, hello. Just a quick test. Can everyone hear me and everything sounds like it's a good volume? Perfect. Perfect. Very busy day. Dying slowly. Pretty good, just studying and whatnot. Okay, so a mix of how we're doing. Had a pretty busy day for myself too. Had to get quite a number of things done, and just adulting kind of spit wild sometimes. Alright, so I'm also going to test to see if you can see everything on the board that I'm going to do, so... Hello! Let me know if the video looks good. Type anything in chat, and then we'll get started. Awesome, thank you. Okay, let's see here. A little late for Christmas. I guess you could see it that way, but there is a little bit of wintry decorations in here, but I love using string lights and LED strips to illuminate my space, so I like changing things according to the seasons and like changing the colors and stuff, so. Alright, let's see here. Let's go ahead and get started then. So what we're going to do is we're going to go over the second version of the practice exam that I've made. So if you have any general questions before we get started, feel free to toss them into the chat. If you have any questions as I am going along, toss anything you have into the chat and I'll look at it as soon as I can. Let's see. And then what we'll do is, as we go through this, we may finish this earlier than, you know, how long we may actually go. So we can go over another version of the practice exam on any other questions that you had, any curiosities about, and we can go over any other concepts. So, but we'll go through this practice exam first before anything. Can the questions be uploaded to Canvas? So do you mean the questions that I pitch in on that? Okay, cool. So it is on Canvas. All right, so let's get started then. So on this one, I made 3 different problems. The 3 problems encompass the core, most important concepts. However, it may not encompass every single thing that you've actually learned. These are just the major ideas. These are, if you have to focus on anything, these are the most important ideas. Now, of course, when I make the problems, you may find that some of these might be a little bit more difficult than what you might find on the exam. I'm not quite sure because I don't make the exams, but I've tried to give you some core ideas to think about. So, on the first version of the practice exam, relating to the first version of the practice exam, rotate. If you're talking about the pulley on the first version of the practice exam, we used a sphere as a pulley. So I believe that because there was a lot more mass on the incline, I think it was 50 kilograms compared to 15 hanging, and the incline being not I guess, too steep, it would tend to pull the system down the incline, and then the hanging mass would go upwards. So that's how I selected the directions based on that. But I'm going to start running through this one, and then by the time we get to the end of this practice exam, we can go through and touch on any other details on the other practice exam or any other questions that you have. So for this one, so you have a fun roller coaster ride that has thrill seekers in a cart with a total mass of 2,000 kilograms. The cart passes through point A, labeled here at the beginning, which is 6 meters higher than point C. So here's point C. It's the lowest point that you end up using in this problem. So this is going to be a reference point. Point A is 6 meters higher. Now the cart moves from point A to point B, when the cart will then drop down this hill through a total of 40 meters to point C. So from point C up to point B, it's a height of 40 meters. During that process, you have 55 kilojoules of its mechanical energy be converted into internal energy, in other words, heating things up in the process. It is known that the kinetic energy of the cart at point B is negligible, so we're going to assume that there's no kinetic energy at the top of the hill here. Okay. First thing we're going to find out is what the speed of the cart is as it moves through the lowest point, in other words, point C. So here's how we want to set this one up. So, hello again. We have this hill here. So just sketch out the hill briefly. Okay. So I have this point here, C, this point here, A, and the top of the hill is going to be referenced to as B. So distances, we have the distance from here to here. From the lowest point up to point A is 6 meters. Drawing is not quite to scale, but then from point C all the way up to the top of the hill, point B, we have that that's 40 meters. Okay, so that distance is 40. And we know a couple of things, so I'm going to write down that the kinetic energy at point B is 0. So KB is 0. And we want to find the speed of the cart at point C. So I'm going to write that I want to know what the speed V at point C is. Okay, so let's find that. Now, we know that we have information about the energies of the system at different points, or we want to know something related to the energy of the system at a particular point. So for instance, if we want to know information about the speed of the cart at any particular point, we could talk about its kinetic energy. Because we have information about the height in the system, we have something about its gravitational potential energy. So we can relate the energies of the system at any particular point using the conservation of energy, knowing that the energy needs to be conserved in the system. So, well, what I will start out by writing is the conservation of energy. Okay. Conservation of energy, I'm going to do it between points B and point C. You can pick any 2 points, however, you want to pick a point that you want to know something about, and you have to relate it to a point that you do know something about. So for instance, because we know something about the potential energy at the top of the hill and its kinetic energy, we can use that as a point of reference to connect the information to, and then we can relate it to point C, which is where we want to know something about. So I'm going to write out generally that in the conservation of energy, the work done by non-conservative forces is equal to, now we can summarize it as a change in the mechanical energy of the object, but mechanical energy is just kinetic plus potential energy. So it's a change in the kinetic plus a change in the potential energy. Depending on how you've used the conservation of energy, this may or may not be exactly what you're familiar with. This is a very general form of it. What you may find in a lot of problems is that, for instance, if you expand out your delta K into final minus initial, if you do kinetic energy final minus kinetic energy initial, and you expand out your potential energy as final minus initial again. If you move this stuff around, you might get something that looks similar to the following. K initial plus U initial plus the work done by any non-conservative forces is equal to K final plus U final. So what I've written here is pretty much the same as this equation right here, but this may be a starting point that you may have used in the problem, or perhaps the work done by non-conservative forces was 0 and you recognize it as all the initial stuff equals all the final stuff. So it's pretty much the same equation. So what I'm going to do is I'm going to use B as my initial and C as my final. So the way I'm going to write this out, okay, is the work done by non-conservative forces equals change in kinetic energy I will expand out as final minus initial, so it's going to be final is C, so I'll say that's my final, and B is my initial. Okay, so we have KC minus KB, final minus initial, plus the change in potential energy, which is gravitational in this case. So same thing, final minus initial, UC minus UB. Okay. Now, I'm going to recognize that anytime I talk about kinetic energy, it has to do with movement. So if it's not moving, then it has no kinetic energy. Also, for the potential energy, since it's gravitational in this case, I'm only going to be talking about height. So if I have height, I have gravitational potential energy. But if I don't have any height with respect to some reference, you set somewhere to be your 0, then that would be the criteria for no potential energy. So what I'm going to do in this problem is very easily, I'm going to set the lowest point that I'll use in the entire problem as the 0, our ground basically. So all the way up down at point C, since we don't go any lower than point C, let's just easily set that as y equal to 0. Okay. It doesn't matter where you set the y equal to 0 in the problem, you'll get the same answer, but it just makes your life a little bit easier if you set it in a sensible location, such as the lowest point, or perhaps the starting point, or the ending point. So now, when we look at all these different terms in the conservation of energy, so let's start at point B. At point B, we have no kinetic energy at the top of the hill. We're saying that it's neglectable. So I'm going to get rid of the kinetic energy at the top of the hill at B. So that's because the speed at B is 0, pretty much. Now, for the potential energies, if we look at the potential energy at point B, there is a height above the y equals 0, so we do have potential energy, so we leave that one alone. At C, we should have movement because the car would have rolled down the hill, so it has acquired a speed, so it's got kinetic energy, but it's at the lowest point, which we've set to our height as 0. So the potential energy at C is 0, and that's because the height, y, at C is 0. So we're simplifying a little bit of the work here. Now, speaking of the work done by non-conservative forces, I did state in the problem here, if you look over here, that as it rolls down the hill from B to point C, basically you'll have that it will lose 55 kilojoules of mechanical energy. So the work done by non-conservative forces is this that I give you here, but you have to recognize that it is a loss, so it is negative 55 kilojoules. So we won't cross that term out, we'll leave it alone. Now, in the event that, for instance, I give you a force, okay, and that force is non-conservative. It could be like friction, it could be tension, any other force that's non-conservative that does work. You could use the equation for work as, you know, a product of your force, distance, and some angle. You could use that to calculate the work done by a non-conservative force. But in this case, I just give you directly what the number is. So what we have left, we have the work done by non-conservative forces. I'm going to expand out what's left. So our kinetic energy, we want to remember it's 1/2 mv squared. So it's 1/2 mvc squared. We have minus the potential energy at B, so minus. Potential energy is mgy or mgh for the gravitational form. So mgy b. Okay. So now all I have to do is solve for my speed at point C. So I'm just going to move some stuff over. So I have the work non-conservative plus mg yb equal to what's left, which is the kinetic energy, so 1/2 mvc squared. I'm going to get rid of the 1/2 by multiplying by 2 to both sides. I'll simultaneously divide by the mass. So we have, on the left side, it's 2 over m. So we multiply by 2, divide by m, and then to this entire left side in parenthesis. Okay. Now, this is equal to the velocity squared. However, we can just square root the whole thing. So we get the square root of all this is the speed at the bottom of the hill. Assuming that you plug in all of your numbers correctly, so we let the mass be equal to 2,000 kilograms given in the problem. The work non-conservative is plugged in as minus. Now, because of how you can just take a unit prefix like kilo and you can just replace it with the correct power of 10, it's best to just leave it as 55 and then just insert the power of 10. So I'll do 55 times 10 to the third joules. So that's negative 55 kilojoules. So that's, again, negative because we had a loss in mechanical energy. G is a given value. Whenever you see G, it's always the gravitational constant, which is plugged in positive. B is the height at the top of the hill, is 40 meters above our reference point. Okay. So we plug in these values, and the answer that you should get for this is 27 meters per second. So the speed at C equals 27 meters per second. Okay. So that's part A to the problem. Let me know if you have any questions on how part A was done before we move forward. So type anything into the chat, and then we'll move forward in a minute or so. If everything looks good, then just let me know. Why is the work negative again? Okay, because the work done by non-conservative forces, we have a loss in mechanical energy. So if we read the problem again, so let's go back to the problem. So here, at point B, when the cart will then drop down the hill a total of 40 meters to point C, and 55 kilojoules of its mechanical energy will be converted into internal energy. So let me actually rewrite the conservation of energy this way to help you understand why there's a minus sign on that again. Okay, so what I'll write is that, let me do it right here. Okay, so if you want to compact the conservation of energy further, so we have that the work done by non-conservative forces equals, now kinetic energy plus potential energy by definition is mechanical energy. So K plus U is the mechanical energy, which we'll call E. So what I'm going to say here is from this form right here that I wrote out, if I state that K plus U, the total kinetic and potential energy in any situation, is to be defined as, I'll use the letter E, and I'm going to say that represents the mechanical energy. Okay. That means that if I have a change in both of them, in other words, delta K plus delta U, that would then be defined as a change in your mechanical energy. So what this then means is that the work non-conservative is equal to delta E. We're just replacing this entire right-hand side. And so if we are talking about a change in mechanical energy, if we take that mechanical energy and we toss it to another form of energy, internal energy to the system, so thermal energy, for instance, that energy would have to leave the mechanical energy and go to being, heat. So that means that it has to lose that in order for it to be transferred somewhere else. So what it lost is what another form of energy gains. That's why in this case it's negative for your delta E, if that makes sense. Let me know. And if there's any questions, let me know. Awesome. All right, let's go to the next part. Part B. If you tried doing this out already, you'll find there's not quite enough space, so you'll probably have to do it on the back side of the paper. Suppose that after point C, okay, so referring back to the original diagram, here's point C. As the cart moves along the track from left to right in this picture, basically we're after point C now. After point C, the cart has lost another 329 kilojoules of its mechanical energy due to internal energy along the way to a new location, call it point D. Okay, so not drawn in the picture, but there's a point D somewhere beyond the picture after you pass through point C. At point D, the cart will move through a horizontal section of the track, which has the same gravitational potential energy as point C. The cart will be slowed down via regenerative braking from a system of linear induction motors. So these are a lot of extra details that you won't need to solve the problem. Just wordy. That can be modeled as a can be modeled as a modeled as compressing a spring having a spring constant of 500 newtons per meter. Calculate the stopping distance of the cart, neglecting any losses of mechanical energy during that process. So let's pick this apart a little bit. I'll sketch this out and I'll sort the information out. So all right, so in this particular case, so we're saying that after point C, so whatever happened from point C onwards, whether if it went up a hill, down, wherever it went, eventually you arrive at some point, call it D. And at point D, we know that it has the same gravitational potential energy as point C. Now that's also another way of saying that the height of both points is the same. So if we drew this horizontal line all the way over to point D, it would basically connect with point D. So regardless of what the track did between C and D, you end up at the same height. Now, let's see here. From point D, continuing onwards to point E, okay, we are told that from point D to point E, there's a couple of things that happens. So the first thing is that during this section, there is no work done by non-conservative forces. In other words, there's no change in mechanical energy here. There's no losses, whereas from C to D there was. Now here, during this flat section, we also are saying that there is this system that we're modeling as compressing a spring. So I can draw this mass that will arrive at point D and this spring. Okay. Now, I guess I should take this out a little bit further because the mass will eventually stop at point E, and when we want to find that stopping distance from D to E. And then the string will stretch all the way to here, where it's probably connected somewhere. Okay, so a few things I'll write include from C to D here, the work done by non-conservative forces, or the change in mechanical energy, will be negative 329 kilojoules. From D to E, the work non-conservative is 0. No change in mechanical energy during that section. We also know that the potential energy at B, gravitational-wise, so let's call this gravitational, I'll subscript it with G, is the same as the gravitational potential energy at point D. So that's C and that's D. And because this is flat, technically it's the same all the way to E. So gravitational potential energy to E is also the same. Okay, so it remains constant. So in order to figure out what distance from here to here, okay, call it X to point E. In order to figure out that distance, you have to realize that you're compressing a spring that stores potential energy, and that's related to what kinetic energy it got by the time you got to point D. So if you can find the information about what the cart has by the time it gets to point D, you can find information about point E. So we'll use the conservation of energy to relate those things. Now, we don't know what this car is doing at D very much. We know more about what's happening at C because we solved for the speed from the previous part of the question. So let me write here also that the speed VC is 27 meters per second. Okay. So let's figure out something at point D. Let's see if we can figure out how fast it goes by the time it gets to point D. So to do this, I'm going to repeat conservation of energy again, but I'm going to do it from C to D. So we state that the work done by non-conservative forces equals change in kinetic energy plus change in potential energy. And this is from C to D. We do have work done by non-conservative forces. We do have a change in kinetic energy that we're going to expect because we're going to find probably a different speed at point D. So we're going to solve for something inside of the kinetic energy. There is, however, no change in the potential energy ultimately. So that means here we can just get rid of this term here. We don't even need to expand that term out. It's because we said the potential energy at C is the same as the potential energy at D. So this implies no change. Okay? So why expand it out if it's not changing? So we only have these left. I'm going to expand out the kinetic energy into final minus initial. So we have that the work non-conservative equals final, which is 1/2 mv final squared, or point D, minus 1/2 m the initial squared, or point C. We basically know everything except for the speed at point D. So let's solve for VD. I'm going to move this term over to the left side here, so I'm going to move that kinetic energy over. So we have work non-conservative equals, or plus rather, 1/2 m VC squared, and that's equal to the leftover term, which is equal to 1/2 m VD squared. So we're going to again multiply by 2 to this side, divide by m, so we have 2, and then divide by m to all of this. And it's equal to the square of the velocity, so we'll just square root it. So we have the square root of all of this is the speed at d. So we know everything in this circumstance. So again, we plug in the mass as 2,000. Work non-conservative in this section is minus 329 kilojoules, or put it in scientific notation, work non-conservative equals negative 329 times 10 to the third joules per kilo. And then the speed at c we found previously was 27 meters per second. We plug all those values in, and we get that the speed at point D is 20 meters per second. And we should expect something slower than 27 because we had work done by non-conservative forces along the way. We had a loss in mechanical energy from the system. So that takes it out of the kinetic and potential energy, so that by the time it gets to point D, since there was no change in potential energy, then we definitely had to have a loss in kinetic energy. So that loss in kinetic energy is reflected by the slower speed. So you have to get an answer slower than 27 meters per second, otherwise it doesn't make sense. Now, once you get this, we're going to do conservation of energy one more time. We're going to do it from D to E, and we're going to connect the information about its kinetic and potential energy at D to its kinetic and potential energy at E, in which we can solve for this stopping distance. Okay. Before I go on to the next step of this, let me know if you have any questions. If you're good, toss it into chat, and then we'll move to the next part of this question. Cool, got it. I'll give you a few more seconds to soak in this information. Looks good so far. Okay, let's carry on. So now, let's rinse repeat this again. Now, technically, if you really wanted to, you could go straight from point C all the way to point E. You just have to account for everything that happens along the way in one shot. So, for instance, if you did a conservation of energy where C was your initial and E was your final, you could do that. You would just need to account for all of the non-conservative work along the entire path to your destination, and you would have to account for both your gravitational and your spring potential energies also in one shot as well. So you can do that all in one step if you want to. I chose to break this down to maybe help you understand what's happening along the way, but it's not technically necessary. Now, given that I did find the information at point D, let's go to point E. So we'll repeat this one more time. So work non-conservative equals change in kinetic plus change in potential energy, and this is from D to E. So again, let's go through. Now in this case, from D to E, we know that there is no change in mechanical energy. So we can say that the work non-conservative is 0, and we can just cross that out to make it a little bit easier. We do have a change in kinetic energy because the cart will go from point D, but the spring is going to do work against it. The spring doesn't want to compress from its natural length. So if you model as compressing a spring, the further you go to the right, the more the spring will resist its motion to the right. So it pushes to the left and it slows it down so that it stops by the time it gets to point E. So it does ultimately change its kinetic energy between D and E. So we do have that term. And the change in potential energy, now in the previous parts we only talked about gravitational, but we have to remember that every time you talk about a change in potential energy, it technically refers to a change in all forms of potential energy. So what we mean by that is that this delta U technically breaks into at least a couple of things you can add together. You can write it as a change in gravitational potential energy plus a change in spring potential energy. So add both of the changes together of both types of potential energy and you get the overall change. So every time you see this, you should always think of both. Okay. For the previous parts, for instance, we didn't have a spring, so we just didn't talk about it. So when we talk about potential energy, what we meant was gravitational potential energy. But since we have a spring here, we will have to consider the spring now. But in this part, there is no change in gravitational potential energy because it's a flat horizontal surface. So we can cross out any gravitational potential energy change, and we can say that all potential energy change in this section is only due to the spring, period. Now, for what's left, we'll expand out. Left side is 0. The change in kinetic energy will be K final, which is now at point E. So KE minus the initial, which is point D, KD, plus a change in spring potential energy. So this will be UE minus UD for the spring. So 0 equals, actually before that, let's cross some things out. So point D, we are moving, so we do have kinetic energy, so KD is not 0. Let's see here, the spring potential energy at point D. Now, because the spring is initially uncompressed, so it's not stretched nor compressed, we use x as that distance it's stretched from its equilibrium position. In this case, since it's 0, we can say that the potential energy of the spring to start with is 0. So because x at point D is 0. No stretch or compression. Okay. So we can get rid of that. At point E, we know that we want the object to stop, so it has no kinetic energy. We can get rid of KE. Because it's stopped. And we do have the spring potential energy at E because we have now compressed the spring some distance. So we have stored potential energy in it. Now, I'm going to move the stuff around a little bit before I plug in, just to show what I'm saying. If I move the kinetic energy D over to the left side, it says the kinetic energy at D equals, and we only have potential energy at E. This is a very simple statement, but it reads aloud the following. All of the kinetic energy that you had at point D was converted completely into spring potential energy at E. That should make sense. So when you move the conservation of energy terms around, it should kind of make sense where your energy is going from and to. We can plug in and expand these out. So it's kinetic energy is 1/2 mv, in this case at point D squared. And the spring potential energy was 1/2 kx squared, where k is the spring constant, not k for kinetic energy. So the way I distinguish that is by making the k slightly different. If you want to use like a Greek letter kappa as your quote-unquote k, it's the spring constant. And then your x, which is the compressional or elongation distance of the spring, squared. We can get rid of the 1/2 from both sides, and we just need to solve for the distance x that the spring is compressed. So, therefore, the spring compression is equal to 1/2 are gone. We divide by the spring constant over to the other side. So we get mass times the velocity squared divided by the spring constant. But then we need to square root to isolate the distance. So we square root this. Okay. Plug in your mass as 2,000 kilograms. The speed at D, which was 20 meters per second from what we got previously. and the spring constant is taken to be 500 newtons per meter. So we plug those in, and your stopping distance or compressional distance of that spring model is going to end up being, in this case, you get 40 meters. So this is an example of how you use the conservation of energy to solve for different pieces of information relating to either speed, compressional or stretching distances of springs. You can use it to calculate the height that things will go to. Anything that you would otherwise feel like you would need to use kinematics for. Instead of using kinematics, you would probably want to lean towards conservation of energy to solve your problems. So let me know if there's any questions on this part, and then we'll wrap up this problem and we'll move on to the next one. You have a question. Will this video be up for rewatching later? Yes, but it will take a little bit of time before it's rewatchable. If this live stream goes on for about a couple hours, you should expect at least the same amount of time after the live stream is over before it's up fully. So it's either going to be late tonight if you end up being a night owl like me, or if you get up in the morning tomorrow, it will definitely be up by then. YouTube does this weird thing where it partially uploads it, so if you watch it before it's fully uploaded, you'll only get to watch part of the live stream, so give it a little bit of time and you'll be able to rewatch the whole thing, but by tomorrow morning for sure it'll be up. Cool, you're crystal clear. That's awesome. Okay, so let's take a look at the last part of this question. For the last part, this one's a pretty simple one. Calculate the average amount of power created from the regenerative braking in the linear induction motor system over a time interval given, 4.51 seconds, that the cart takes to come to rest, assuming 100% efficiency. When I say 100% efficiency, it means assume no losses along the way. So we just take the definition of power and then we just plug it in. So there is a little bit of a twist here that you'll need to see. So we'll take a look at that. So let's let me do this. Let's erase that part out. So we want to calculate the average power created from the system. So we have that the power, by definition, is the amount of work done per amount of time. So that's going to be our average power. So average. If you want the instantaneous power, you need to do dw dt, the instantaneous rate of change, the time derivative of the work done. So the average power is just simply amount of work over amount of time elapsed. Now, I do give you stuff pertaining to the work, such as the work done by non-conservative forces. Now, the way that you can look at this is that, okay, so if this is ultimately just the net work done, it's also stated from the work energy theorem that the net work is equal to the change in kinetic energy of the object. So another way that you can actually reformulate the power is to actually say that if this is the net work done, then it's also the same as a change in kinetic energy over time. Technically, we're going to do the absolute value of this to get the power produced. So if you know more about the change in something's kinetic energy, you can say that's caused by some amount of work done on the object. So in this case, if we're going to calculate the power generated from D to E that goes into a system outside of our cart moving along the track, we can just refer to its kinetic energies instead. So we can say that it's equal to K final, which is KE, minus K initial, which is KD, divided by the time. We know that we are stopping at point E, so we can just get rid of the kinetic energy at E. And we are still taking the absolute value of this. So it's just negative the kinetic energy at D. So we say it's negative 1/2 mvd squared divided by the time. You use the same mass. The speed at D. Speed at D is, what was that, 20 meters per second. You use the time as 4.51 seconds. Okay. So when you plug those numbers in, you take the absolute value. The power that you get from this, now if you just pull this off of your calculator and you have it in scientific notation, the number that you're going to get immediately is 8.87 times 10 to the 4th. Now, when you run through the units, you end up getting amount of energy or work done in joules divided by time in seconds. Joules divided by seconds is defined as a watt. So we say W for watt. If you want to express this in kilowatts, you just move the decimal point over and drop the power by 1. So this is the same as 88.7 kilowatts of energy. Let me know if you have any questions on this part or anything about this problem, and then we'll move on to the next problem. Everything looks good so far? No questions? Okay. Okay, so let's take a look at, oh, there's a question. So you have, the mass I plugged in was the mass of the cart, correct? Yes. I've used the mass of the cart of 2,000 kilograms. And the reason for that is because I am talking about the kinetic energy of the cart. So the change in the kinetic energy of the cart uses the mass of the cart. And if you want a little bit more details about exactly what was going on in the problem, because I technically told you that we were modeling the system as a spring, there is actually no spring physically present there. You may find that oftentimes in problems you do in real life, you may want to look at models that you can use to approximate things. We're saying that the motor system is pretty much the spring. So when we say that we're storing potential energy in the spring system, what we actually meant was that we were transferring the energy into the motor system. Will it be different if it's not 100% efficiency? That is correct. So realistically, in a given situation in real life, nothing's going to be 100% efficient. So what may happen is you may have some losses. You know, for instance, when you transfer the energy from one place to another, if it's electrical, there may be something like electrons moving through, you know, different wires, and they create heat when they do that. So, you know, you may have some losses and non-recoverable energy that goes to heat, basically. So if you have something like it's 90% efficient, it means that you take 90% of the ideal answer. So if we had 88.7 kilowatts, you would take, for example, 90% of that answer of what's recoverable. Okay, so for number 2, you have a firework which is launched into the air. briefly comes to rest at its highest point in the path. So I just drew a little tiny picture for that. At that moment, it explodes into two pieces. The masses are given, so a smaller piece and a larger piece. The larger piece is found to be moving with a speed of 20 meters per second immediately after the explosion. We're going to calculate the speed of the smaller piece immediately after the explosion, given the information about the larger piece. So with this one, you could almost think of it as like an equal and opposite to reaction sort of thing. That being the case, when you're talking about Newton's third law with equal and opposite reaction, that is a circumstance in which you can apply the conservation of momentum because it comes directly from it. So in this case, we're going to apply the conservation of momentum to solve this problem. Yeah, no problem. This one's not too wild of a problem. It's a pretty straightforward one once you realize you just need to apply conservation of momentum. The collision problems are probably something that will require a little bit more work, and yeah, so I would say that if you study a lot of collision problems, it will help you to really prepare for how to deal with a conservation of momentum. So I've seen it on many different tests that I've taken and that I've seen other people take. So it's a good problem to look at the collision one. But here's another basic conservation of momentum problem. So I want you to kind of expand your horizons beyond just doing collisions. So for this one, you have the two masses. So we have a smaller mass, we'll call it M1, and we have a larger mass, let's call it M2. It doesn't really matter which one you call 1 and 2 as long as you're consistent with your 1s and your 2s. One of them will shoot off one way with one velocity, and the other one shoots off the other way with another velocity. Now, just conceptually, you should already understand that for the momentum to be conserved in this system, if you have the bigger piece moving away with some velocity, some speed, the other piece, the smaller one in this case, has to compensate the other way, meaning that if it's a smaller mass, it should be the one that ends up moving faster in that case. If it is, in this case, like an equal and opposite reaction, the smaller piece should go flying off. So whatever we get for our answer for the smaller piece, we expect a higher speed than the bigger piece. So the conservation of momentum states the following, is that the total momentum of the system is conserved, meaning it stays constant. So we say the total, or the sum of all momenta initially, equals the total or sum of all momenta final. That's just the condensed way to write it. Otherwise, it expands out as P1 initial plus P2 initial, because we have two objects in our system, so we do two momenta. That same thing is going to be on the other side, but final, so P1 final plus P2 final. The definition of momentum is mass times velocity, so we expand out each of the terms as mass times velocity. So we state that it's M1 V1 initial, expanding that term out, and the same for all the rest of them. So M2 V2 initial equals M1 V1 final plus M2 V2 final. Okay. Now, technically, you didn't have to expand them all out. You could have realized that if the momentum is based on its movement, if it's not moving, then you wouldn't have a momentum. So you could just say from here already that if the system before the explosion, which is our initial case, before the explosion, nothing was moving at all, period. So in that case, if nothing was moving, you could have actually crossed out both of the initial terms already. So we can just get rid of these. Okay, so the left side is just 0. 0 equals m1 v1 final plus m2 v2 final. Now, we want to solve for, in our case, we've labeled the smaller mass as m1, again, just being consistent. So since we labeled it that way, we're going to solve for v1 final. So v1 final, we'll move this term over to the other side. So we have minus m2 v2 final equals m1 v1 final. We divide off by that mass to isolate the velocity. So we have v1 final equals negative. I'm going to write it this way. It's m2 over m1 times v2 final. I've written it this way to emphasize the relationship of what happens. Notice that the answer to this problem just depends on what the ratio of the two masses are. So if I had just simply told you that one mass was 3 times bigger or 3 times smaller than the other mass, then you would know that the velocity output is just going to be 3 times smaller or 3 times bigger. So you don't technically need the masses precisely to get the answer to this. So in my case, mass 2, which I've labeled as the bigger one, mass 2 is 0.75 kilograms, whereas m1 is 0.25 kilograms. So it is 3 times bigger. So when you have 3 times bigger of a mass, you get 3 times more velocity for the smaller mass. So in this case, you get minus so 0.75 over 0.25, which is 3 when you divide it, times the speed of the larger mass, which was 20. Velocity of the other mass. Now, this answer ends up being 3 times bigger, which is negative 60 meters per second. Now, this technically is the velocity, so the minus sign indicates the direction relative to the other one. So in this case, notice that the answer being negative means that it's moving in the opposite direction of this one. So if you treated the line of motion for both objects as like an x-axis, one of them will be moving in the positive x and one of them will be moving in the negative x. Now in this problem, so this is directional, because I ask you for the speed and not the velocity, the subtle difference is that the speed is just how big the velocity is, the magnitude of it. So we don't account for the direction in the speed. So the speed, which I'll just indicate by the absolute value bars here, is just positive 60 meters per second. And that's what we're looking for. Okay. Let me know if you have any questions on conservation of momentum and applying it to this problem before we move on to the next part. Okay, relatively good so far. Okay. Part B is to just calculate the amount of kinetic energy that is lost from the system upon exploding. This word right here was a little typo. This should actually be a gain of kinetic energy, which you'll see in a second here. Another way I could have worded this was to just simply find the change in the amount of kinetic energy of the system. A change could be positive or negative. Positive meaning a gain, negative meaning a loss. In this problem, we'll find that it's a gain because you'll notice that before the explosion, the objects are stationary, so they collectively have no kinetic energy. However, once they explode and they go off in opposite directions with their respective momenta or velocities, they will both have a kinetic energy that is non-zero, which will add up to a positive number. And if you had more to end with than what you started, then the change is positive. So it will not be a loss. It will be a gain. So let's take a look at how we calculate this out. It's pretty straightforward. So we'll need both of the masses and both of the velocities because the kinetic energy depends on both of them. So the change in kinetic energy, you know, how much you lost or gained, is going to be delta K. You can call it delta K total or delta K system, whatever you want to label as to indicate that we're accounting for both masses in the system. I'll call it total. There's two ways of actually doing this, which arrive at the same conclusion equally. You can write that change of the entire system as the change in 1 plus the change in 2. In other words, delta K1 plus delta K2. That's one way of approaching it. So for delta K1, you would do K1 final minus K1 initial, and the same thing for 2. Or you can also write it this way, is that the change in anything is just final minus initial. So you could say what's K total final for 1 and 2 and subtract it with K total initial. Okay? They both mean exactly the same thing. So whichever way floats your boat, you can do it either way. I'm going to do the bottom way. So I'm going to calculate the K total final and the K total initial. Now, this way actually makes it easier because notice that if I wrote it in this form, you would have a change in both because 1 starts at rest and it begins to move, and 2 also starts from rest and it begins to move. So there is a change in kinetic energy of both of them individually. You can't cross out either of those terms. But if you choose to write it this way, as final minus initial, well, the total kinetic energy of the system to start with is 0. So you can easily just get rid of that entire term. And it actually makes it look a little bit cleaner if you do it this way. So it's good to think of it both ways. So we're going to get rid of this term because we have no kinetic energy before the explosion. And then the K total is just the kinetic energy of 1 final plus the kinetic energy of 2 final to add up to the total final. So K1 final plus K2 final, which is just 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. So just plug in your kinetic energies into both terms. And we have all the values, so you just plug in. We let M1 be, that was our smaller mass, so it was 0.25 kilograms. Mass 2 was 0.75 kilograms. It doesn't matter if you make the velocities positive or negative in this case because kinetic energy is always going to square your velocities anyway. So it doesn't really matter what you write here for 20 meters per second. So we'll just plug in these values here. And when you plug in those values, you get the following. The change in kinetic energy of the system total equals, it ends up being a positive number as expected. It's 600 joules is what I got. So this is how much kinetic energy that was either lost or gained into the system. In this case, it is a gain. So positive implies gained. Okay. Let me know if there's any questions on this part of the problem. If we're good, let me know, and then we will go on to the last part. Looks like we're good. No questions. Okay. Okay, there is a question. In the problems, we are usually given regarding collisions, is there ever a change in energy? I'll add in a little bit of wording to your question to make it a situation that you would have, because when you say change in energy, more specifically what you would be referring to is a change in mechanical energy. So if I quickly wrote out here for, if you deal with collisions, for example, when you talk about a collision problem and you want to talk about, let's say, is the energy conserved? So now if you say just energy broadly with no specifics, you don't say, kinetic energy, potential energy, any specific form of energy. Technically, the energy is always conserved, meaning that the energy will just go from one form to another somewhere else, whether or not you can use that form of energy, whether if it's mechanical or if it's internal energy of an object. So more specifically, what you might mean is, is there a change in its kinetic energy, or is there a change in its mechanical energy? And the answer to that is sure, because during perfectly elastic collisions, you'll find that there is no change. And if it's not perfectly elastic, there will be some change in that mechanical energy of the system. So if you wrote out the conservation of energy, you could say work non-conservative is a change in mechanical energy of the object. And when the collision occurs, you can have that, for instance, objects will deform, for instance. Like if you have two vehicles colliding, now some of that energy has to go into, deforming the different parts. So that energy will not be recoverable. So it is a form of non-conservative work that is done. So, for collisions that are, I want to say, perfectly elastic. So perfectly elastic. Okay, you'll find that the work done by non-conservative forces are zero. So therefore, the change in mechanical energy to the system will be zero. Okay. That would then imply, if you're talking about two objects moving along a straight line towards each other and colliding, you could then talk about specifically that change in mechanical energy being a change in kinetic energy of the two object system. Now, else, okay, meaning if it's not perfectly elastic, meaning that there is some degree of inelasticity, whether if it's an inelastic collision or a perfectly inelastic collision, you would have that the work non-conservative forces not be equal to zero, and therefore you will have that there is some change to the mechanical energy or the kinetic energy of the system, so you'll get an answer that's not zero. It turns out that if the collision is perfectly inelastic, that number is actually maximized. You have lost the most amount of energy from the system due to work non-conservative. So hopefully that answers your question. Let me know if that makes sense, and then we'll carry on. Physics mug. Perfect. Awesome. Makes sense. It's not coffee if you're wondering about that. It's actually tea. I don't really like coffee, so. Part C of this, if the explosion occurred 50 meters above the ground, and it is found that the smaller piece moves straight downward, hits the ground with exactly the same speed that it immediately had immediately after the explosion, how much of its mechanical energy did it lose due to air resistance? So this, you're talking about energy. and how it converts from one form to another, that should automatically ring conservation of energy. So we're going to use conservation of energy to this, but the part that might sound a little strange is that, okay, well, the explosion occurs, and okay, so we're talking about the smaller piece, okay? We know that the smaller piece in the explosion moves away from the explosion with an initial speed of 60 meters per second as found in the first part of the problem. Now, you would expect that as the piece falls, it would speed up as it loses potential energy as it goes down to the ground, but you would, in exchange for that, gain its kinetic energy, which means it should move faster. However, realistically, there is things like air resistance that will convert it into other forms of energy. So what we're saying here is that it hits the ground with exactly the same speed that it had immediately after the explosion. Now, what this could imply is that, for instance, it could start out at 60 meters per second here after the explosion. It could initially, let's say increase as it falls. So it could go up to like 70 meters per second. But as there's air resistance, what might happen is, it might go back down to like 60 meters per second. It might try to slow itself down again. So because of air resistance, we could have that it hits the ground with exactly the same speed, or maybe it could hit the ground with a slower speed, depending on the situation. So let's use conservation of energy to solve this part. So we have that there's an object up here, and here is the ground. Okay. So the object is assumed to go straight vertically down towards the ground. So we're going to say it follows this path here, okay, and it reaches the ground. So this is going to be our initial. This is going to be our final. And we're going to apply the conservation of energy from there to there. So we get from the conservation of energy that the work non-conservative equals change in kinetic plus change in potential energy. Because I told you that it hit the ground with exactly the same speed that it had immediately after the explosion, the change in kinetic energy from initial to final is ultimately 0. So that might sound a little weird at first, because I just got done saying that, maybe it did change its speed along the way. It could have gone from like being 60 to 70 midway, and it could have slowed back down to 60. There could have been some change in its speed along the way. However, when you're doing delta, meaning final minus initial, that doesn't care about what happens along the way to its destination. It only cares what did it start with and what did it end with. So if you ignore all the details in the middle, 60 meters per second at the top, 60 meters per second at the bottom, no change. That's it. So there is no ultimate change in kinetic energy. So this means that the work non-conservative, in other words, let me rephrase that, the work non-conservative is the work done by the air molecules against the object, so the air resistance, the air friction. That work done by the air is the change in potential energy, which is in this case gravitational, because there's no spring present in the problem. It's just falling. So if I could just calculate what its change in gravitational potential energy is, that's it. That's all we're asking for. Now, if we expand that out as final minus initial, so U final minus U initial, and we know that it's gravitational potential energy, which needs a reference point set, it's pretty sensible to set your y equal to 0 at the lowest point in this case, which is just the floor or the ground. So we can say that the final potential energy, which is based on the height of 0 in this case, we can just cross out that final potential energy like this. Okay. You can either do this, or you can write that the delta U, the change in potential energy, is just mg delta y, if you really want to condense it down. That's actually what I did in the solutions to this, was use delta y. But this would be, I guess, the more step-by-step way of doing this. So it's negative, and the potential energy, gravitational, is mg, y, initial in this case. So we plug in all the values for this, and we get negative. The mass we're using is the smaller mass, as in stated in the part of the question. So it is 0.25 kilograms times 9.8 meters per second squared times the height initial, which was 50 meters given in the part of the problem. Okay. And when you calculate this out, you find that the work done against the object ends up being negative 123 joules. Negative 123 joules. So this answer being negative means that there was work done against the system. It indicates that, if you know that the work non-conservative is a change in mechanical energy, we're saying that it's negative. So there's a loss of mechanical energy from the system to somewhere else, such as internal energy. Instead of speeding up all the way down, what it could have done, which was speed up, it instead remained the same speed by the end of the path. So it had definitely lost mechanical energy along the way. If there's any questions on this, let me know, and let's do the last part, the last problem. Okay, so this problem is going to be a little bit more involved than the second problem. But this is going to be dealing with rotational motions, so rotational kinematics and torque. So with this one, you have a 20 kilogram bucket of water that's attached to a lightweight rope, which is wrapped around a solid cylindrical pulley at a radius of 0.25 meters from its center. So here's a little sketch of the pulley. I have this pulley system. There is an inner radius and there's also an outer radius, which I'll explain in a second, but your bucket of water is attached by a string or rope which is connected to some radius. I tell you the pulley itself is a larger radius than where the rope is actually attached, which is why the diagram is like this. So at a smaller radius of 0.25 meters, the rope is attached there with the bucket, and the whole pulley itself is actually 0.35 meters to its edge. Now, I give you the radius of the pulley and also the mass of the pulley. If a person pulls on the rope wrapped around the circumference of the pulley, meaning the very, very edge of the pulley, okay, so that's this rope here, in such a way so that the bucket of water slows down at a given rate of 0.25 meters per second squared. Pay close attention to the fact that that's an acceleration, not a speed or velocity, because I'm telling you it's slowing down at this rate. So it's a change in the velocity over time. So it slows down at that rate while it lowers down into a well. So this bucket is dropping in the diagram, but it is slowing down on its descent. We're going to find what force of tension must the person create in the rope. So meaning basically what is the tension they need to pull with at the circumference of the pulley in order to satisfy lowering the bucket down at this rate of acceleration. So I'll sketch this out real quick and we'll make a free body diagram of this. Now because it's a rotational system, we're going to consider torques acting on that pulley. Okay, so we have our pulley, which I'll draw here. Here's the pulley. We have a point of attachment at a smaller radius than the radius of the whole pulley, where you have this bucket of water hanging down like this. I'll call this hanging mass mass 2, M2. And you also have the rope at the top, which pulls up the circumference, which, again, it doesn't really matter exactly how you draw this, so as long as there is a mass hanging at this radius, and you have another rope which is pulling at the full radius. So in this case, the full radius I just drew at the top. Okay. If we draw all our forces acting on the system in order to find the tension that the person is pulling with, we identify that the tension that the person is pulling with has to be the one rope at the circumference. So we say that there is a tension T1 applied there to the left in this diagram. Because there's a rope hanging here, the rope is tugging on this pulley, so it's creating another tension. So we say that there's a tension downwards, T2, on the pulley at a different radius. Now, because there's another mass here, this mass over here could have its own free body diagram that determines its linear motion up and down, because as this pulley system would have the ability to rotate, let's say that, we know that the bucket of water is lowering in this case. As this bucket lowers downwards, this whole pulley system has to rotate clockwise, like that. So the system will spin clockwise in order to lower the bucket downwards linearly. So you can see that there's a relation between how this pulley rotates and how this mass linearly translates. So connections between rotational motion and linear motion. Now, so in order to find our tension T1, we consider that this is one of the forces that applies a torque to this pulley. So we want to consider what torques we have on the pulley. Ultimately, we're just using the rotational form of Newton's second law, which is the sum of all torques equals the moment of inertia times the angular acceleration. This is perfectly analogous to your more famously known form, which is the sum of all forces equals mass times the total acceleration of the system. So it's pretty much the same thing, but this is translational or linear. This is rotational. So we have two forces that are acting on our pulley system. Now, technically, there is a third force, which I will draw in, but it doesn't cause any torque. There's a third force here that tries to pull the pulley straight down. This is the center of mass of the pulley at the center, and when you have a mass distribution, a mass spread out in different locations around a common axis of rotation, you'll have that the weight of the entire system could be modeled as acting at its center of mass, which is in this case at the direct center. So I could say that it's the mass of the pulley times g, so that's the weight of the object. But because that is the axis of rotation, and the weight or any force that acts at the axis of rotation, because of that torque acting at that distance being 0 from the axis, there is no torque exerted onto the system. So we ignore this force here. These two forces do cause torque, but we do need to set up a coordinate system that's consistent. And you do have to be a little bit careful here, because now you could go with the idea that in a standard rotational coordinate system that counterclockwise is positive by definition if it's not otherwise stated. But technically, with coordinate systems, the only thing that really matters is your consistency. You can change that coordinate system around. So for instance, I could say that instead of counterclockwise being positive, I could define clockwise as positive instead. And as long as you're consistent, the physics will work out. Now, let's say I do go with the convention that counterclockwise, anything that tends to move the system counterclockwise is taken to be as positive. And in terms of angle, that will be increasing angle or positive angles. What I mean by also being consistent in the entire system is that you have to realize that this rotational motion is directly linked with the linear motion of this bucket and the linear motion of this rope. So you cannot just arbitrarily say, oh, I want down to be positive on this mass. You could do that in theory, but the thing is since that you've already selected counterclockwise to be positive on the pulley, that corresponds to motion upwards on the hanging mass. So this has to be positive upwards. Let's call it the positive x-axis. It has to be positive upwards so that it can flow counterclockwise. And then up here on this rope, if we do need to discuss it, motion to the left is also positive. So notice how the positive consistently flows in the system. If I had, for instance, set positive to be clockwise, I would have to move this arrow to the right, and I would have to flip this to being down positive if that were the case. So be mindful of your coordinate system and how the direction flows. Now, that means when I have these two forces here, T1 is going to cause the system to have a tendency to rotate counterclockwise, but T2 will have a tendency to rotate the system clockwise, so they kind of fight each other. So the torque created by T1 is positive, and the torque created by T2 is negative. So I'm going to say that it's torque 1 positive, and then minus torque 2. That will be my sum of all torques on the left side. I handled the left side and the right side separately, so if that's my left side, my right side will be moment of inertia, but I do state that it's a solid cylindrical pulley. Now, we don't exactly tell you that, you know, here's the moment of inertia for a solid cylinder, but what we do tell you is that the moment of inertia for a solid disk is given. Specifically, the moment of inertia of a solid disk is 1/2 the mass of that disk times the radius of that disk squared. Now, why would I use the moment of inertia of a disk in place of a cylinder? The reason for that is that when you have, you know, a disk, okay, and your axis of rotation goes through the center of that disk like this. So here's your axis of rotation right through the middle of the disk. And you spin that disk around that axis of rotation. The moment of inertia is 1/2 mr squared. Now, the thing is that the moment of inertia depends on how you distribute your mass away from that axis of rotation. So whether if you choose to put this mass, you know, let's say you have a mass on the very edge of that disk, if you were to shift that mass downwards to a new point over here, it's not going to affect the moment of inertia because it's the same amount of mass located an equal distance from the axis of rotation. The distance away here is the same as the distance away here. So you could literally take all of the mass in that disk and you can spread it downwards so that it makes a cylinder. And the thing is that you have the same amount of mass and all masses are still equally distant from the axis of rotation. So spreading the mass along the axis of rotation, elongating the shape out, does not change the moment of inertia. So the moment of inertia of a solid cylinder is equivalent to the moment of inertia of a solid disk, as we would say. So, you know, the disk equals basically a cylinder. Okay. So that's our moment of inertia, I. Now, the angular acceleration, it would be more helpful to write another way because I gave you information about the acceleration of the problem. I stated that the acceleration of the bucket was a magnitude of 0.25 meters per second squared. Now, that acceleration of this bucket translates into up and down motion of it. It's linear motion, so it's a linear acceleration. but we know that as this pulley rotates, this object translates at the same time. It goes with it. So it's, it's distance that it moves, it's velocity, it's acceleration. All of those linear quantities are very closely related to all of the angular quantities based on the radius. That's literally the only factor separating them. So I can change this angular acceleration in terms of linear acceleration, which is a over r. So I'll write ax, the acceleration along the x-axis for this hanging mass, divided by its radius that's hung at. So in this case, the radius 0.25, not the radius of the whole pulley. So notice the distinction between the capital R for the whole pulley and the lowercase r for where you hang that mass at. Now for these two torques, you do need to expand it out further, so you have to then say that the torque, tau, can be defined as the distance from the axis of rotation, which we generally write as lowercase r, but we will use whatever radius we see fit, times the force perpendicular to that radius line. So the thing is that in my diagram, my axis of rotation is right in the center. The application of force at this point, you would have this line directly connecting it to that point of application of force. That is the radius line, and that is your distance r that you use in the torque. Force perpendicular means to take the component of the force that's perpendicular to that radius line. So in this case, since this force is straight down and this radius line is out to the right, it's already perpendicular, so you just use the whole thing. But let's say in the event that the force is not perpendicular to that radius line, you have to find the perpendicular component of it, so you'll use like an angle and split it into like a sine and a cosine in order to get your force perpendicular. And you'll just plug whatever that force perpendicular is into the equation for torque. So if we use this for torque 1, let's say, now torque 1 is based on this tension at the top, which is perpendicular, so it's good. But we are using the whole radius because this force is applied at the circumference of that pulley. So we use capital R times that force of tension for the first torque. So we say that it's torque 1 equals the whole radius, capital R, times the force perpendicular, which is tension 1. That will be the first term that goes into T1, or tau 1. Now for torque 2, so minus, torque 2 is applied at the smaller radius, so I will use lowercase r times the force perpendicular, which is in this case tension 2. Okay. So we've substituted for both of our torques. This is equal to the right side, which is still the same thing, so 1/2 mass of the pulley, radius of the whole pulley, capital R squared, times the linear acceleration divided by the smaller radius. So now we need to solve for T1 because T1 is what the person is pulling with. So we're going to move this term over and we'll divide by the radius capital R. So what we get is that in solving for T1, you get 1/2 mass of the pulley, radius of the entire pulley squared, the linear acceleration divided by the smaller radius. We add over this term, so we plus the smaller radius times tension 2. We divide the entire thing by this bigger radius, capital R, to isolate the tension T1. So this expression correctly solves for T1, assuming I did not make any mistakes. And the values you plug in are the following. Is you say that the mass of the pulley is given as I think it's 1.5 kilograms. So 1.5 kilograms. Yeah, it's 1.5 kilograms. We have the bigger radius is Is it 0.35? I think it's 0.35. It is. The small radius is 0.25, both in meters. The linear acceleration, now this is where you have to be a little bit careful. It turns out if you do make a mistake here, you won't end up getting it incorrect based on what most people would do. The acceleration linear is directional. It could be up or down. The thing is that because mass 2 is dropping, and I told you that it's slowing down, in order to slow an object down that moves along a straight line, you have to point an acceleration in the opposite direction. So in this picture, as this object moves down, to slow it down, something needs to be accelerating it upwards. So with an acceleration upwards translates to the value being positive. Now, if I were to do something as simple as change the wording to it accelerates downwards, it speeds up, for instance. If I were to change it very simply to that, an acceleration downwards would have meant that its value is negative, not positive. So you have to mind the value of the acceleration based on your coordinate system. So do be careful with that. In this case, the acceleration does end up being positive because it is directed upwards to slow down the object which moves down. So the acceleration is positive. I'll write the plus sign to emphasize the direction. 0.25 meters per second squared. We have, let's see here, the radius, T2. The only thing you end up missing here is T2. So you can't quite fully plug in everything. You have everything but T2. So from here, you need to find what T2 equals. Okay. So you can do this by just looking where else T2 appears in the problem. So we need another equation for T2. We look in this diagram, we say, okay, T2 appears here, which is where we were using it as a torque. Now, this is where I'm going to complete the rest of my diagram, which I should have done earlier. The other mass is the hanging mass, and you have a weight, m2g. And because this is the same rope here, the same section of rope, there is another T2 pointing up. Okay, so there is a T2 pulling down on the pulley. Equally, there's a T2 pulling up on the mass. So the tension will always point away from the mass in question and along the string of rope. So you'll find that they kind of point towards each other on either end depending on which mass you're asking for. So here's our free body diagram for mass 2, and we find that there's a T2 on that. So if we just do a Newton's law on this mass, we can find what T2 is in terms of some known information from the weight. So T2, we will then say, is from the sum of all forces. Notice we're using forces, not torque here, because it's linear motion along the x-axis equals mass 2 times the acceleration along the x-axis. I'm going to handle the left side separately from the right side. The right side I will leave alone. On the left side, I'm going to plug in my sum of forces. I have, keeping in mind the coordinate system being positive upwards, we will have that T2 is upwards, so it's positive, and the weight is downwards, so it's negative. So I'm going to say it's positive T2 minus the weight, m2g. So this gives us the other equation that we can then use to solve for the tension. So we find that the tension, T2, is simply adding over that term. We get m2g plus m2ax. So now that we have this expression for the tension, which we do know the mass, hanging, and we do know the acceleration, we can plug it back into where we needed it, which was right here, and we can finally get our T1. So if we plug that in, the expression that we get is T1 equals 1/2 mass of the pulley, radius of the pulley squared, linear acceleration divided by the smaller radius plus the smaller radius times this expression here for T2. So quantity, don't forget to distribute, or you can leave it in parenthesis at least, m2g plus m2ax. Okay? So that whole quantity is T2. All of this is then divided by the radius of the pulley, capital R. Okay? At this point, you do have everything, because we are also given that the hanging mass is 20 kilograms. Okay. So plugging in all of these numbers in will lead you to the following result. T1 ends up being 144 newtons. Okay. Now, before you accept this answer, there's a couple of checks we're going to make. The first check I'm going to make is a check for the units, because you might be confident that you've moved the equation around a lot, but I'll tell you that even after 6 or 7 years of doing physics, you still make really, really silly mistakes, and it doesn't have anything to do with how much you know. Things such as minus signs, which are really everyone's worst enemy. We'll have one single minus sign buried inside like 6 pages of work, and it just screws everything up. Your signs, moving things around wrong, it just happens. So if you check your units, which only takes 30 seconds or less to do, you can get a better feel for if your answer is more likely to be right or wrong. Because if the units don't work out, then you know that you moved something around wrong in your algebra. So quick unit check on this. Notice that you are looking for a tension which needs to end up in newtons, so you do need units of force to end up at the end of this. So if you analyze the units, for instance, in the top, you have kilograms. This one's meters per second squared, so the mass and the acceleration give you a newtons here. There is a meter squared and a meters on the bottom, which will give you an extra meter, so it's a newton times a meter in the top here. All of these, this is a newton times a meter, this is a newton times a meter. So the top is all newtons times meters added together. The bottom, you're just going to divide out the meters. So all you're left with is newtons, and that allows you to then say, okay, this expression is reasonable. It makes sense. I've had tests before where my units don't work out, and I was able to fix my mistakes because I actually checked the units very quickly. So it's worth doing that check. The other thing is this answer actually is reasonable because it's in a ballpark of other forces. So for instance, the whole system here is being driven by gravity. So gravity is trying to pull this mass down. If you look at its weight, the weight is 20 kilograms times about 10. So 20 kilograms times about 10 is about 200 newtons. This is in the ballpark of that. So we can kind of get a reasonable ballpark check for our answer as well. So let me know if you have any questions on this first part, because I know there's a lot that you are solving and moving things around. So let me know if you have any questions, or let me know if everything makes sense, and I will move on to the next part. Question: how come there's 2 different tensions even if it's the same rope? I thought the same rope gives you the same tension. The long story short on that is that now in this problem it is 2 separate ropes. Okay, so there's a rope that now if you want to be precise about the details, there's a rope that's wrapped around at a smaller radius, and it uncoils and unravels out this bucket that's hanging. That's separate from the rope that's wrapped around the circumference. So there's definitely 2 separate tensions in this problem because there's 2 separate ropes. But in the problems where you do have the same rope, for instance, in the first version of this practice exam, there is one single rope that winds over the pulley. And now, even though it's the same rope, you do get two different tensions on the two different sections because you are accounting for the rotation of the pulley. It basically now it has a moment of inertia compared to previous cases where before we talked about rotation, it did not have a moment of inertia. So in order to accelerate this pulley, in order to give it an angular acceleration, there has to be an imbalance in the torques. And so you would have, two different sections of rope, and you would have to say there's a T1 and there's a T2, and those tensions would then be different to create an imbalance in the amount of torque. So you have more torque trying to spin it clockwise compared to maybe less torque trying to spin it counterclockwise. And that will ultimately give you a net torque, which, according to Newton's law, will angularly accelerate the system. Given that the tensions would be equal to each other at the same radius, that would mean the torques are equal. And with no net torque, you would ultimately have no angular acceleration of the pulley. So that's as much as I could summarize that question. Let me know if there's any other questions for this part of the problem. Another question, a couple more. Can you go over again the coordinate system? It's usually where I struggle most of the time. Okay, yeah, definitely. I'll even give you a variation example to kind of show you how I get the different coordinate systems and how I work with them. And then the other question is related to that one about the acceleration being negative since it should be driven by the force of gravity, which points downwards according to our coordinate system. Why is the acceleration the positive x? Okay, I'm going to tie those two questions together. There are definitely questions that a lot of people actually do struggle with. So let me point out a little bit more in detail what that was. So let me go back to this problem right here. I'll explain it in the context of this, and I'll give you the version A of the practice exam to then realize what you would do with that. So in this problem, so first of all, okay, so I'm starting with the pulley. Okay. Now I don't have to start with the pulley, but I'm going to go with the pulley convention because we do have a convention for it that positive is counterclockwise and negative is clockwise. So let's say that you go with the convention. The convention being counterclockwise positive, anything that tends to spin it counterclockwise or is spinning counterclockwise is defined to be positive. Assuming that to be true, remember that the linear motions, of this object here, and let's say if I had another object over here, or you can just think of the rope that's moving left to right here, the linear motions of the attached pieces directly correspond to the rotational motion of the pulley. You spin this pulley counterclockwise, this object lifts up. You spin this clockwise, that drops down. They are interconnected with each other. So in order to be consistent for the entire system, you have to have that whichever way this pulley is spinning, let's say positively, has to correspond to positive motion of this hanging mass. So this winds counterclockwise, positive, this has to move up, also positive. So it has to be consistent with the flow of the rotation. Now, to go into why the acceleration is positive as opposed to negative, yes, gravity is driving the system. However, there is one more influence on the system, which is you. You pull on that rope and create a T1. That actually fights gravity. So this is ultimately a battle between gravity pulling the bucket down and you trying to keep the bucket, from falling down. So the acceleration could actually go either way depending which one is going to win in the end. Now, in many problems, we would have you solve for which one wins in the end, which is a way of saying what's the acceleration of the system. If you find your acceleration to be positive or negative, that determines which way it's going to accelerate ultimately. So for instance, if I pulled hard enough with T1, it would beat out whatever weight is hanging from that pulley. So if I was beating out the force of gravity, then I would expect that the system will accelerate up here to the left. This rotates counterclockwise, and that lifts the object up, or at least tries to lift it up. So let's just say it accelerates up. If, in the case that gravity wins and I'm not pulling hard enough, then the acceleration of gravity would win and cause the acceleration of the system for this hanging mass to go down, the pulley to go clockwise acceleration, and for my rope at the top to be accelerated to the right. So again, they're all linked together. But in my case, because I stated in the problem directly that two factors, let me write those factors down real quick. I first stated that one, bucket is dropping or lowering. Okay, that's the first point. So because I know the linear motion of this object is downwards, so let me indicate that here. I'll draw this velocity arrow to the side of it. Actually, let me do it right here. Here's my mass, m2, and I'm only going to draw the velocity for now. So I know its velocity, v, call it v2, is directly downwards. Now, if you're only talking about motion along a single axis, which our axis is vertical in this case, so here's our axis here. If you're driving a car, let's say, your direction of motion is, let's say, this way, okay? If I'm driving this way and I want to speed up the car, you would have to point an acceleration in the same direction to cause it to speed up. If you want to slow down, I would be moving this way, but my acceleration will be the opposite way from the motion in order to slow it down. Now, if you want another scenario, you could change its direction by pointing an acceleration perpendicular to its line of motion. That's where you get into circular motion. But in terms of this problem, because the motion of the object is downwards, the acceleration, in order to slow it down, which is what I stated in the problem, the acceleration has to be opposite to its motion, so it has to be upwards as opposed to the motion being downwards. So this picture will slow down the mass over time. And because my coordinate system was positive upwards, positive x upwards, that's why I stated the acceleration was positive, very specifically. So hopefully that clears it up. So the other thing I was going to say from here is that, so one condition was that the bucket was dropping down, but the other thing that allowed me to figure out the direction of the acceleration is that I told you that the speed is slowing, or let's say decreasing. Okay, so these two statements together will tell you the information of the acceleration needing to be upwards ultimately to slow it down. So let me know if that makes sense. And actually, hopefully that's enough. If you need to see, actually, let me draw up the other example real quick, just so you solidify the coordinate system for the other practice example, and then I'll make sure you're on the same page. So very quickly, the other one here with the incline, okay, pulley and your masses. This is how you select your coordinate system. Again, how you choose your coordinate system is completely up to you, but the only thing that you need to do is be consistent. So let's just say that, you know, let's say that we expect M1 to move to the left down the incline. So what I'm going to do is I'm going to, by default, select positive x in the direction of motion that I expect. So if I expect motion down the incline, let's just say that's the direction of positive x. That must mean that this rope is going down the incline positively, but in order for the pulley to keep up with that rope, that pulley has to spin counterclockwise to wind up the rope and go down the incline this way. So that corresponds to counterclockwise motion. So that means positive must be consistent with this. But as you're spinning pulley counterclockwise, that also lifts up mass 2. So that means positive must be upwards on mass 2. Equally, if you don't want to do it this way, I could have done positive x up the incline, positive rotation clockwise, and then motion downwards on this being positive. Okay. Notice again the consistency. That's what matters in the end. So now let me know if you have any questions, if that's clear now, and then let's finish the other parts of this problem. You're good. Awesome. Okay, I think we are good. So, A was the longest part because you have to solve out the whole system. The other questions pertain to the rotational kinematics. So, next one is, what is the angular acceleration of the pulley? There's a couple ways you can get this. So you should be thinking of rotational kinematics. So there are Kinematics Equations, which include things such as your angular displacement, delta theta. There's at least 2 kinematic equations you'll have, anywhere up to 4 of them. I end up using 3 of them. I'll write them out on the board in a second. But there's also equations that relate angular motion to translational or linear motion too. So there is, for instance, an equation that relates. So let's explore that for a moment here. So let me write down the kinematics equations that I personally use. You'll find that you can either add one more to this list, or you can even take away from one from this list, and you'll still be able to solve the system. So let me write the 2 essential ones first. So under the condition of constant acceleration, so assuming constant acceleration, okay, then the following will be true. You have the angular speed final equals the angular speed initial plus the angular acceleration times the time. This is perfectly analogous to your linear kinematic equation, which says that the final velocity equals the initial velocity plus the acceleration times the time. The other essential one is that the change in angular position, or the angular displacement, is the angular speed initial times the time elapsed plus 1/2 the angular acceleration times the time elapsed squared. Okay? If you have these 2 equations, you can technically solve the problem. Now there's a third equation that I personally also use because there are circumstances which it is useful and saves me a little bit of time. This one is the angular speed final squared equals the angular speed initial squared, angular velocity rather, plus 2 angular acceleration times the angular displacement. With these 3 equations, you'll find that, with this extra equation on top of these 2, you'll be able to solve problems no problem. And this third one will be useful in a number of circumstances, which will speed up the process. There's a fourth one, which I'm not going to write, but it has to do with the average of the 2 angular speeds. So they have these available to me. Now, you should also keep in mind the relation between translational or linear motion and angular motion. So these equations connect the 2 together. So on one side of the equation, I'll write linear, and it's a translation to rotation. So we have that, for instance, the distance, delta s, traveled along a straight line. It could be like delta x, delta y, whatever you want, but a linear distance is just the radius times the angular distance that you move, or the angular displacement. The linear velocity is the radius times the angular velocity, and the linear acceleration is just the radius times the angular acceleration. So if you want to relate between rotational and linear motion, especially in our case where we're literally rotating our pulley, will translate into linear motion of a dropping object. You can use these equations to connect the two kinds of motions to each other. So for our case, in this part of the problem, I will be using this one here because I told you what the linear acceleration was, and you know the radius that it's applied at, so we should be able to easily find our angular acceleration without going through the kinematic equations. So if I solve for the angular acceleration, it's the linear acceleration divided by the radius it's at. We know that it's 0.25 meters per second squared, positive in our coordinate system, so remember plus and minus is based on the coordinate system, divided by the radius that it's applied at, which is also 0.25 but meters. So we just get 1 for this. So alpha is, now you'll notice that everything cancels except for the second squared. Now the technical unit that takes its place, even though it's technically unitless in the top, you can call it radians. So it's radians per second squared. So this is equal to 1 radian per second squared. Radians do not technically have a value as a unit, so we regard them as unitless. Now the following parts just use this acceleration to solve for other things I ask. So for instance, if you look at the other parts here, if the initial speed of the bucket is 10 meters per second, keep in mind this is a speed of meters per second, meaning it has to be a linear speed, especially if I'm talking about the bucket. How much time will it take to bring the bucket to rest? So now this sounds very much like a kinematics problem. Now, so if we do use the kinematic equations for this, because we do have information about a speed, we want to know how much time it takes based on some acceleration we have. So we should be looking into these. Now the thing is that I don't give you the angular speed omega. This is the angular speed omega, but those are in radians per second for a rotating system. I told you that the bucket is moving at 10 meters per second, but that's linear motion. So in order to get it into rotational motion, I use these equations to convert between one and another, so I can say that for this part of the problem, I want to use the relation between linear velocity and angular velocity. And I will say that our angular velocity is the velocity linear divided by the radius. I'm going to call it initial because it is the initial in our case. So omega initial and v initial. And this equals linear velocity. Now be careful with your signs because again, these quantities have direction. It can move up or it can move down or side to side. So for the bucket, positive is up, but it's dropping. So if the velocity is down in a coordinate system that has that positive is upwards, the velocity must be written as negative. So this is negative 10 meters per second, and then divided by the radius that it's at, which is 0.25 meters, and that gives us that omega initial is negative 40. Again, the meters cancel out, but the unitless ends up being expressed as radians for your angle per second. Okay, so now we get this angular speed, but we now need to use this angular speed to get our, in this case, we need to find our time that it takes to bring it to rest. So I will then sort this information out with the following table. I will write that because in these three equations you will only see 5 things, You can distinguish the 5 things in these equations, so I'll list out. We can have some angle we turn through, omega initial, omega final, alpha, and time elapsed. So I'm just going to organize my information in that table. I do not know how much angle the pulley turns through in that time. I do know my angular speed initial is -40 radians per second. It will come to rest as stated in the problem, so we know that at the end of this, the bucket will stop, but the pulley will also stop rotating likewise. The angular acceleration was previously found to be 1 radian per second squared. Okay. And the time is unknown, but we want to find what the time is. So I'm going to put a little star next to the time to find the time. So what we're going to do is we're going to pick one of these kinematic equations that avoids any other things we don't know, which is the angular distance or displacement. So we're going to try to avoid using theta. That means if we're going to avoid using theta, I will try to then use the top equation. Okay, so the top equation, I'll write that down. Omega final equals omega initial plus alpha delta t. We can cross out anything that's 0. So for instance, the angular speed final is 0. We can solve for alpha. So we get that. Or not solve for alpha, solve for t rather. The time elapsed is negative omega initial when you move that over and you divide by the angular acceleration, and it's negative. Omega initial is -40, so the negatives cancel. Radians per second. And your alpha is 1 radian per second squared. So everything cancels out except for seconds left over, and you just get that the time is 40 seconds. So let me know if there's any questions up to this point, and we'll do the last part to this problem. And this will wrap up the practice exams, so if everyone looks good on this so far, then we'll do the last part. So most of the stuff comes from knowing how to arrange your information. Yep, and that's pretty much what it is in a lot of the physics that you do, is just knowing how to organize your information. Especially, you know, if you, let's say you rewind back to the very beginning of this class, when you're first learning physics especially, what I find in a lot of people is that people have trouble with physics largely because they don't know how to properly organize their information. So the lack of organization is often the downfall, which is why word problems are such a struggle for a lot of people. But especially in these problems where there's like a consistency with the equations that you use, you realize there's only 5 kinematic quantities that you use in your kinematic equations. It's easy to just, you know, lay out a table of information of this, all the stuff you could possibly use. And then realizing, you know, here's what I have, here's what I don't have, and then just picking an equation that you know fits the situation based on the things that you have and you don't have. Typically, what I will do with the kinematic equations is I will say that if I do not have something other than the thing I'm trying to find, I will avoid using the equation that doesn't help me out. So for instance, I chose the top equation because it didn't have delta theta in it. I didn't know anything about the angle, so I just wanted to avoid it if it was possible. So yeah. And let's just look at the last part, and then we'll wrap it up, because I know it is getting a little bit later, and then a couple of people have already left. So last part here. How many revolutions will the pulley turn through by the time the bucket comes to rest? So when I'm asking for how many revolutions, it's equivalent to asking you for what's the angle that the pulley turns through. Revolutions is another way of saying basically what's the amount of angle. Because one revolution corresponds to an angle of 360 degrees, which is the same as 2 pi radians, which is what you ought to be using, not degrees. So what we're going to need to do is find that angle that it passes through and change it over to revolutions. So here's how we're going to do that. So using our kinematic equations, we're going to solve for the angle delta theta, or the angular displacement that the pulley turns through. Now I'm just going to update this table of information so that now, because I have the delta t, which is 40 seconds, I'm just going to do this problem with 40 seconds as a known value. Now, there's a couple ways you can think of it in terms of solving this. Using these kinematic equations, you can actually take 2 routes. You can actually go with equation 2, which does have delta theta in it, or you can also go with equation 3, which also has delta theta in it. And you have everything else, because this whole table is filled except for the thing that you want. So, but here's the difference, I would say. Here's the pros and the cons. If you go with equation 2, it's already solved. That's a positive, so you don't have to move anything around. So that's one possible place that you would make mistakes, is by moving things around. But there's a little bit more stuff to plug in, so, you know. But now the other thing is that it does require the time. Because it requires the time, let's just say you're taking the exam. If you get the answer to the previous part wrong and your next part relies on the previous answer, then if the 40 seconds was wrong for some reason and you use equation 2, well then guess what? Your answer for this one is also wrong. Now your method is good, which gets you most of the points, but it's technically wrong in the end. If you choose to do equation 3, however, notice that it wouldn't matter if I got the answer to the previous part. So even if I got the previous part wrong, it wouldn't matter, because I'm not using that information. So now the downside to this equation, though, is that you do have to move things around. So it's kind of, you pick your poison, basically. Would you rather move stuff around, or would you rather rely on your previous answer? So I'm going to use this bottom equation. So you pick. You'll get the same answer either way. Now, I will get rid of the angular speed or velocity final, because it does come to rest. So I will set the left side to 0. Omega initial squared plus 2 alpha delta theta. We're going to move over the first term as a negative, and we'll divide off by 2 alpha. So that solves for delta theta. Delta theta equals negative omega initial squared divided by 2 alpha. In this one, you get minus, so angular speed or velocity initial is negative 40 radians per second squared. I'm sorry, not per second squared, it's per second. This whole thing is squared. One of the most common mistakes in these problems is to forget to square something. So make sure to double check that you squared everything. So if you're spending a little bit of extra time on your test checking your work, try checking everywhere that has a square. You might find that you forgot to square something. Even if you wrote it, you might have not squared it in the calculator. So be mindful of that. I've just noticed that from many, many students, that they just forget to square. 2 alpha, so we have 2 times 1 radian per second squared in the bottom. 40 squared is going to be, 40 squared ends up being 1600. 1600 divided by 2 ends up being 800, so your delta theta. Now the negative signs don't actually cancel here, because the negative ends up getting squared before you have the negative here. So it's technically negative. Now the reason why it's negative in our case is because, again, paying attention to the coordinate system, if positive is counterclockwise, a negative angular displacement means that the system is being rotated clockwise, which makes sense because the bucket is being lowered. I can't remember if I did put a minus sign in the solution, so it technically does need to be negative. Now, you do get radians left over, though. This is the answer other than you left it in radians when it's being asked for the number of revolutions. So here's one last thing. It's a conversion. However, a lot of people make a mistake on this, so watch closely. 800 radians times conversion factor. I need to cancel out the radians, so I do 2 pi radians on the bottom and 1 revolution on top. Okay, so this will give me in revolutions. However, here's the thing that most people do wrong. When you take, for instance, a standard calculator like this, and you, for instance, do 800 divided by 2 pi, and there's a button that says pi on the calculator, so you can just do 2 times pi. Now, the problem with this is that when you don't put the 2 pi in parenthesis, the calculator reads it from left to right, and it says 800 times 2, divided by 2 times pi, when you're not doing that. You're dividing by the whole 2 pi, not multiplying by a pi. So you either need to put the 2 pi in parenthesis, or you can just write 6.28, which is 2 pi. But if you don't do that, your calculator is going to give you the wrong answer. So I'd probably tell you about half the people get this wrong, surprisingly. Just a very simple thing. So make sure you mind that. In any case, the answer that you do get for this, when you do 800 divided by 2 pi properly, gives you 127 revolutions for this. Okay. So the pulley turns through 127 revolutions clockwise before it stops. Okay. So if there are any final questions on this problem, let me know, and let's wrap it up probably. We'll go from there if you have any questions. Right now we're sitting a little bit past 10, so it seems like a fair place to stop, but we'll just play by ear. Are there any more questions on this problem? If not, are there any questions on anything in general on this practice exam, or anything a little bit more broad? And then maybe from there we'll end it. Now, before anyone else starts heading off, I want to remind you that I do have my hours tomorrow before the class in the regular room and time. So if you have the time, drop by, and we're going to review a little bit more before your exam. So yeah, so that answers your questions. So yeah, drop by tomorrow from 12 to 2 in that time frame in the same room. I'm not sure if I can get out another practice exam by then. If I can, then we will go over a third version of the practice exam tomorrow, but that's maybe slightly optimistic, so we will review it either way. And you're welcome. Looks like we're mostly good. All right. Yeah. So I think we're pretty much set. It's getting a little bit later, so be sure to get some rest. Just a tip from me is that, I used to be someone who got like only 3 hours of sleep before an exam, and the more I go forward, the more I realize it actually hurt me more. So get yourself a little bit more rest than what you might think you might need, and it'll probably help you to cram tomorrow when you need to. You'll have that energy to keep on going. So no more questions, so you're welcome, and thanks for tuning in. And feel free to drop any more questions in the chat, but I'm going to end the stream. So I'll see you hopefully tomorrow. Otherwise, best wishes with all of your studying.